Well, thank you, Michael, and HebrewU, and thank you all for staying to the bitter end. Today's talk, I tried to put a biblical allusion into the title here, because I think sometimes, maybe the people in this room, we think of ourselves as networking people, and if we recruit graduate students, we are graduate students, we say, what do you study? I'm a networking person, I do networking. And I think it's counterproductive for a field that's about connections to wall itself off from other fields. And I think what I'm going to tell you about is that.
So where does the title come in?
Well, this is
the title. No, I was wondering if that was an explanation of that.
I'll probably stick to the limited theological parameters that I'm comfortable discussing here. So what we found, what my students and collaborators and I have found, is that there's a lot of benefit that can come by sort of pushing the boundaries of what it means to do networking research. And in particular, we find that it's worth refactoring the interface between things that talk to the network and how the network talks to the application. So in particular, between the codec and the transport, it's worth refactoring that interface. In general, anytime we can break up, the stuff of computing, functions and resources into small bits, and provide a sort of functional interface to them where state is explicit and change is explicit, it's going to enable new applications, which I'll tell you about. In general, this idea of being able to save and restore the state of a program, or maybe restore it somewhere other than where it was first saved, it's a very powerful tool. So I'm going to tell you about 4 systems. I sort of only have one trick, but we just do it over and over again, which is this idea of taking something that's implicit and making it explicit, putting a sort of functional interface on it, and then using that to save and restore states of a program in different places. So I'm going to tell you about how we did this for image compression, distributed image compression, how we did this for highly distributed video compression, low latency video compression, how we did it for real-time video, like video conferencing, like a Skype or that kind of application, how we're going to try and do it for parallel make, like make-J5000, run 5,000 compilations in the cloud for pennies. And I think you already heard from Dima. This is my name for Dima's. He has a more modest name for his own tool, but I just call it the Dim agent. Which is sort of the same trick applied to security, where we want to save and restore the state of an SSH client after we've locked in the limited authority in order to achieve sort of limited delegation of authority. So it's the same trick 5 times. I only have one trick, which is about sort of saving, restoring, or taking something that's implicit and making it explicit. All right, and please feel free to interrupt at any point. All right, let's talk about the first one, distributed image compression. This was at NSDI, and this is with a former Stanford PhD student and his colleagues at Dropbox. So I did, my friends were at Dropbox, and Dropbox has roughly an exabyte of people's files. Who here uses Dropbox? Yeah, this is being video. I don't use Dropbox, but I won't. It's being videotaped. But anyway, they have about an exabyte of all your files, and they looked, and it's about 35 or 40% of them are JPEGs. So if you're the company and you're paying a lot of money to store other people's JPEGs that probably, by the way, never, ever, ever get looked at. Every time you take a picture, it's uploaded to Dropbox. Most videos on YouTube are never watched. Most JPEGs in Dropbox are probably never looked at. So they're storing all this stuff. They're paying a lot of money. You might ask, well, JPEG was standardized, in the 1980s. So can we somehow save money by compressing these JPEGs more? Now the trick is that Dropbox is not like it's a file system. So you might want to compress these JPEGs, but you can't change the contents of the files at all. It has to be bit for bit the same file. So that was the question that motivated this work. So it turns out JPEG, it's a lossy format. The JPEG looks different than the original, data that came off the sensor, but it's not wholly a lossy format. There's sort of 3 layers. The pixels come in off the camera. There's a discrete cosine transform, which is essentially a lossless stage. Then we divide these numbers by some amount. So we divide by 5, we divide by 8, or if we're feeling very lossy, we divide by 100. And when I say divide, I mean integer division. So we divide and round to the nearest integer. That's the lossy step. That's where we lose information. And then there's another, at the bottom of the pancake, there's another lossless step where the bits are serialized out using a Huffman code. So that's is lossless, lossy, then lossless. So if you were going to try and make this better, the question would be, what if you just change the bottom layer, the lossless encoding, instead of a Huffman code, what if you use some sort of very sophisticated, probably invented in Europe kind of entropy coding? Probably by like a French person, some very smart person, more sophisticated entropy coding, or an Israeli. The smart countries. So could we do this? So it turns out people have tried to do this. So we got to have byte for byte reconstruction of the file. What if we just change the lossless step, the bottom here? So one thing you could do is you could replace the Huffman code, a DC predicted Huffman code, with an arithmetic code, which was patented in 1989, but is not patented anymore. And anytime you have an arithmetic code or even a Huffman code, you have to some probability model that predicts whether the next bit is going to be a 1 or a 0 with some probability. And the more unlikely what happens, the more bits, physical bits, it takes to represent. So if you're pretty sure it's going to be a 1, and it is a 1, that's very easy to represent. If you're darn sure it's going to be a 1 and it turns out to be a 0, that could be very expensive. So that's true of a Huffman code or an arithmetic code or anything. So a lot of the hard part here is in assembling a sophisticated enough, accurate enough model to predict whether the next bit's going to be a 1 or a 0. So we're not the first people who have tried this. So there's a tool called Jpeg Rescan that just rearranges the coefficients from the normal order to this progressive order, and that gets, well, I should explain this graph. So here's the sort of status quo. So the decompression speed is here on the y-axis, so the better speed's up at the top, and the compression savings is on the x-axis. The better savings is to the right. So the best algorithms would be up here, good savings and good speed. Whoops, good savings and good speed. So JPEG, just making it a progressive JPEG, it's sort of a 7% savings, and you can decode that at about 100 megabits per second. You can use an arithmetic code, sort of the standard arithmetic code with the standard probability model. That gets you maybe 14% savings, and you can get it at 40 megabits per second. Or you can be a crazy German person, a single German person whose life's mission is to compress JPEGs, and this dude worked on it very, very, very hard, crazy German guy, and he got, this is being recorded, isn't it? Yeah, okay. Well, anyway, very, very smart German person, and he got sort of 23% compression, and it works at maybe 16 megabits per second on a sort of Xeon, contemporary Xeon. So that's very sophisticated. So it's also an arithmetic code, but you've got a gigantic model. It's like, I think he has something like 300,000 separate coefficients in his model to predict the next bit. It gets very good compression. Oh, and he does these global operations. So he takes all the coefficients and he sorts them. I mean, his program sorts them and it puts them in the right order. And it's a sort of big thing. So if you're Dropbox, unfortunately, this is not good enough. We can't go. I used to consult for them. The company, the servers can't go from serving files very fast and suddenly at like 15 megabits per second, on the full CPU. So but the compression is very good, because they save a ton of money. So the requirements, the other requirement for a yes.
So actually, can you change the model here? Do you have to do this at the Dropbox side instead of they control the app, right? They have the Dropbox application. Can you just send this packed JPEG format and expect the client to do this? Would that be a workable model, or are there constraints that make this impossible or unworkable?
Turns out many Dropbox clients they don't control, like the web interface, for example. So you could imagine implementing this maybe in the JavaScript for the web client and in the iOS client and the Python client. You could imagine doing it that way. It would be hard, though, and that's so far not the way they did. I mean, it would be good because then you'd save bandwidth in addition to saving storage. But they'd have to change sort of every client that ever talks to Dropbox. Use wget the file.
You do that all the time, but Dropbox update has been issued or something.
Yeah, but a lot of people use like wget.
All right, fair enough. The persistent URLs and stuff.
Yeah.
Okay.
Yeah. So they really just want it to be sort of user, not even distinguishable at all to the user. So there's other issues is that Dropbox is, obviously it's a distributed file system. It's not like all the files are in one place. So you have to be able to independently store and decode, if you do this compression, chunks of the file, like any substring of the file. And the compression people, like me, don't get to choose where those chunk boundaries are. It's someone else in the file system that says, here's where the segment or the chunk or the extent of the file begins and ends of the JPEG, and that has to be compressed just by itself, because the server that stores that extent could be in Toledo, Ohio, and the server for some other extent could be somewhere else. These have to be decompressed independently. So you don't get to see the whole JPEG at the decompression time. And you need to get more than 100 megabits per second. And the company, I mean, I didn't care so much about this because I don't have my files there, but the company was very insistent that we not lose anybody's data. That was important to them. So we need the encoder and decoder to both be totally deterministic. It has to be totally immune to sort of evil input files. If you look at FFmpeg, for example, there's a lot of sort of evil MP3s and evil MPEGs that make FFmpeg do crazy things. And that was not, they don't want a story in the newspaper that says, hey, put this file in your Dropbox and then it can't save it, or it erases your hard drive. That was like not okay for them. So we came up with a tool, Lepton, that converts that lower lossless layer from these Huffman code words to a VP8. This is a Google video format, a VP8 arithmetic code. And then we just went totally crazy on the probability model. So that German guy had like 300,000 coefficients. I think we have like 800,000 coefficients. We just like, because he has all these global operations like sorting the coefficients. We can't do that. So we compensated. We can't do that because we don't get to see all the coefficients, when we decompress. We compensated by just making the probability model incredibly gigantic. And then we trained it against real images that were, in Dropbox. But the question is, how do you achieve fast decoding of these independent chunks? And the answer is, we needed to be able to parallelize the decoding and distribute the decoding. And to do that, we formulated the hard part here. Remember, when the user tries to retrieve the file, we're decoding our own format, lepton. Then we have to recode it as a JPEG so that the user gets the same bits. So we formulated that JPEG encoder in explicit state passing style as a functional program where the state of the JPEG encoder is captured at every byte that it outputs. We can discuss the state of the JPEG encoder. And that lets us start encoding in midstream anywhere. So it takes the state as a sort of formal parameter, and even in the middle of a Huffman code word, remember, because we're converting back to an old-fashioned Huffman code, we can start outputting. And so the state has to have everything required to resume printing out that JPEG from midstream. It turns out it's only 16 bytes if you really get down to it. Now, it wasn't, the goal here is to get it as small as possible because we have to put it in these fragments. We sort of had a game about how small we could get it, where the other guy, the former Stanford student Daniel, would come up with all these test cases that we had to do correctly, and then I would try and get the state as small as possible. Say, we don't need that variable, we don't need that variable, we don't need that variable, and he'd be like, wait a second, I think we do need that variable. And I'd say, hey, it passes the test, man. He's like, well, let me find a different JPEG where it doesn't pass the test. So we had sort of like a back and forth. So ultimately, we got the state down to 16 bytes, not such a big deal, and we save the state in our files, and then when we want to reconstitute the file, we just use that state in order to resume re-encoding the JPEG from any point. And there's two benefits of this. Number one, that's what allows us to distribute the decoding across independent chunks that could be on totally different servers, but it also allows us to parallelize decoding within a chunk on a single server to get the speed. So these are the results I showed you before, and then here's our open source program. So it gets almost as good compression as the German guy, not quite as good, but within a percent, and it's like 150 megabits per second. So we actually deployed this at the company. As of the last time they told me, they'd compressed just over 200 petabytes. They turned them into like 150-something petabytes. It turns out, so they set up a cluster to start compressing all their old images, which they're doing at about 6,000 images per second, and that's consuming 300 kilowatts. So the company has done the calculations to say running this program is worth 300 kilowatts. That's based on how much electricity costs them and how much hard drives cost them. I don't know the answer to either of those things, but the company thinks it's worth it. So the lesson here is that a little bit of functional programming, we're talking 16 bytes of state, can go a long way, saving like millions and millions of dollars. We did need that functional codec to be able to deploy this backend JPEG recompression totally distributed in parallel. So that's the lesson on number one. Any questions? We have till tomorrow, right? There's no time limit on this. Okay, great.
No, there is dinner.
Dinner, what time?
7 p.m.
7 p.m., great. Okay, well, I'll just take the next 2 hours. Okay. So that was number one. So that's just like me, a little networking guy comes over. They say, hey, we've got this networking problem. It's a distributed file system problem. But to solve it, we had to know something about JPEGs. And the answer is functional programming. It's the answer for everything. And when I say functional programming, I don't mean like lambdas or Haskell or what those terms actually mean. I really just mean capture the state of the automaton at any point so that you can resume from midstream. That's all I'm trying to say. All right, let's talk about a second application of the same trick, which is video encoding. So this paper is also at NSCI. We got a very expensive domain name. So look, like it's very nice to be able to do things interactively, to be able to edit documents interactively. There's Google Docs, for example, where I could have it on my screen. You have the same document on your screen. If I had an X, that edit to the document happens immediately. The X shows up on your screen. It's instantly, enacted. So like, what if we wanted this for video? Like people tell us video is the most important thing. 99% of the internet is just cat videos. Ankit, I think, told us this, right? So like video's the thing. Well, it's so frustrating to edit video. Like who has ever like edited a video? Was it frustrating, sir? Yeah. So like you make a tiny change. How long does it take before that change is even ratified on your own computer? Like for an hour-long video, it could take more than an hour, right? Yeah. And then how long before someone else can see it? Could be even longer. So this seems stupid. Like we have Google Docs, why don't we have Google Docs for video? It should just be instant. But there's some challenges here. Oh, and you might not just want like edits. You might want all kinds of the beautiful future that all the Silicon Valley people are telling us. So maybe you want to apply some filter to your video, or find a particular person somewhere in the video, or maybe you want to apply some machine learning to eliminate a person from the video. These are all sort of actions that you might want to take on a video in an interactive, sort of playful way. Just like if you had it in front of you. You know, if anyone's ever edited a movie in real life, it's a very visceral thing. Like you have the film in front of you, you put it in the thing, you cut it, you splice it together. Like you really feel it. It's instant. And somehow, like, we don't have this when it's like videos. It's actually faster to work with the film in your hands. Not that you can do this, but maybe, I mean, if it was all old-fashioned, you wouldn't have had this guy in the first place. But we should be able to do, you know, interactive, immediate edits that are immediately shared to the world of audiovisual content. The problem is that we can't re-encode the video. After you make the change, how do you encode an hour-long video? It turns out to encode an hour-long video in 4K, you know, on one computer takes like multiple hours. Or if you buy a chip, they say, oh, the chip's great, it runs in real time. So that means it takes an hour to make one change. Like this is not good. So, you know, if you wanted to run this pipeline on video, it would take hours and hours, even for short video. So the question is, can we achieve interactive collaborative video editing? And what's the trick to get things to be faster? Like, you could be very smart and optimize the single core performance, but I'm not that smart. But you could just use a lot of computers. That's the other trick. So can we do it with massive parallelism? Well, it's not so easy. There's two problems. Number one, somehow you got to get, like, to get the sorts of latency, you know, we're talking about, you'd need thousands of threads running in parallel, and they'd have to be able to start up instantly. So how do you get that? You know, you can't get it on EC2, right? If you wanted to boot up thousands of cores on EC2, first of all those cores would have to boot Linux, you know, which takes like a minute. And then, let's say you do an operation, let's say it's 1 second on each core. But now you have to pay for an hour on all these cores, and you're only using them for 1 second. That's like not very good. So that's problem number one. Problem number two is that even if you have the CPU resources, you can't encode the videos with arbitrary parallelism. Because the more parallel you make the video encoding, the worse the compression gets. And I'll explain why that is. So those are the sort of two central problems of this work. So what we did, number one, we have a framework to run sort of 5,000-way parallel jobs with inter-process communication on these new cloud function services. So Amazon has one called Lambda, Google has one called Google Cloud Functions, IBM has one. So these are intended for sort of web microservices, but we have a framework to run sort of these big batch jobs on them. And number two, we made a purely functional, explicit state passing style version of the VP8 video encoder and decoder to get the sort of fine-grained parallelism so that you can get 5,000 threads worth of, you know, compute out of a 15-minute video. So we call this X camera. So I'll tell you about the framework first for the parallelism, and then we'll talk about the video encoder. So, you know, everyone knows about EC2, I hope. Does everyone know about EC2? OK, great. So EC2, you can get the thousands of threads. You can run arbitrary Linux executables, but it takes like a minute to boot up a core, and you're paying like an hour, you know, even to use it for a second. So if you had 3,600 threads, you know, if you had an hour-long video, you assign one thread for each second of the video. On EC2, it would cost you like more than $20. But these new services like Lambda, they're intended for sort of event handlers and microservices, or, you know, someone pushing a button in a mobile app. But turns out you can get the thousands of threads, you can get arbitrary Linux executables, they start up in less than a second, and they bill you based on the 10th of a second, which is really important. Like, maybe it's not computer science important, but it's like important. Because if you want to run 3,600 threads for 1 second, it costs you 9 or 10 cents. So imagine if you had something that's, you know, some job that's going to take you an hour on your chip. It feels like the application should say, like, look, you could either run this locally, it's going to take you an hour, or you can click this button, run it in the cloud, it'll take 1 second, and it'll cost you 9 cents. You know, it seems like that button should be on like most of our applications, if it really works, which it sort of does. So we built Mu, which is a sort of framework for running these large jobs with inter-process communication. So it starts up thousands of threads in seconds. We have a trick for doing this that involves thousands of TCP connections that we start up very quickly, and it manages the inter-thread communication between these cores because they're behind a NAT, so, you know, there's some bookkeeping there. So it's open source software, so that's the framework for starting up these jobs. And then now we have the threads, but the problem is we still can't get the parallelism to actually use all those threads, because the more finer grained the parallelism, the worse the compressions of efficiency. So why is this? Okay, let's talk about what a video codec really is. Traditionally, you know, there's like a pair. There's an encoder and decoder. On the inside is a sequence of pictures, turns them into some opaque stream of bits. And on the right side, we get some approximation of those pictures back. So the way that these systems save bits is they exploit the temporal correlations between adjacent video frames. So if you're looking at me, you know, the background's the same, my body's the same. So the fact that these adjacent frames are similar is what allows the system to save the bits. Because you know, the series of frames are sort of a series of instructions that say to the decoder, you know, hey, take the last frame you decoded, fiddle with it a little bit, add some change to it, and that's the new frame. And that's very efficient. Yeah?
At least in MPEG, to avoid error propagation, there are what's called independent frames.
Yeah.
So naturally,
So that's all gone.
it's all gone, and now it's one big sequence.
Well, I'll get to that in a second, but the new codecs since H.264 are deterministic. And so there's no more, they're specified down to the bit level at conformance in the decoder. So there's no more requirement in the specification to ever force one of these independent frames.
Yeah, but then if there's one erroneous bit,
Well,
anywhere for any reason, the whole thing goes.
well, you're right, but TLS takes care of that generally for us. It's hard to have a flipped bit on the internet today. I mean, you're totally right. But no, you're absolutely right. So even in these contemporary codecs like VP8 or VP9, they distinguish between frames that are totally by themselves, which we call keyframes. And these are frames that you could resume decoding the movie at, and they stand alone. It's like a JPEG image. And frames that depend on the state of the decoder, which they call interframes. So it makes a big difference. The keyframe in the typical video is like a megabyte, and the interframe is like 25 kilobytes. So you really want to have as many interframes as possible. But there's a problem of the interface. So if you buy a chip that's a video codec, or you get some software that's a video codec, you typically get the same interface, which is there's an encode function that takes a sequence of images, and what it outputs is it always starts with a keyframe, because the decoder has to start with a keyframe, because that's a frame that doesn't depend on anything, and then a sequence of as many interframes as you need. And then there's a corresponding decode operation that's got to start. You got to give it a keyframe to start, and then a bunch of interframes. And what you get back is a bunch of images that approximate the original images. So this is the traditional interface, and that makes it really hard to do fine-grained parallelism. Because let's say we were doing a serial encode of 200 frames. You can give those 200 frames to the encoder, and you get one keyframe and 199 interframes. What if you want to parallelize it by just dividing the video up into a bunch of 10-frame chunks? So you could have 20 threads, each one you get 10 frames, but now each one is outputting its own keyframe and then 9 interframes. So each one is like an extra megabyte. So we end up with 19 extra megabytes to encode this as a consequence of the finer-grained parallelism. The finer-grained the parallelism, the more keyframes, the worse the compression efficiency. So this is sort of like a central dilemma of this video encoding. If you have the interface that they give you, which is that there's sort of this state that evolves along with the encoder, it's hidden state locked up in the encoder. There's no way to sort of start encoding from midstream. All right, so I think you see where this is going. We need a way to start encoding in midstream. So we need access to these intermediate computations, the intermediate state. And the existing encoders don't give you access to that. So we built an implementation of the VP8 format. It's totally compatible with Google's, but it formulates the encoder and decoder explicitly, the decoder as an automaton, where we can reason about the state in between each frame that gets decoded. So at the beginning, the decoder consumes a keyframe, and it emits a picture to display on the screen. But the result is that it transforms itself to being in a particular state that's the result of the keyframe. And then it consumes another interframe. These are like edges on an automaton. And it ends up in a new state, and it spits out a different picture for display. So each interframe is sort of a transition from an input state to an output state. And we reason about these states.
So is the state smaller than the interframe? In the keyframe, it's not obvious why it should be smaller, right?
No, the state's big, but that's okay.
So if you save it, isn't it the same as emitting a keyframe?
I'll get to it. We use the states. We don't send them to the user. That's not part of the compression cost, but we use them as part of this distributed encoder. All right. So what we built was a video codec, an implementation of this VP8 in explicit state passing style. So we have a decode function. It's a pure function with no side effects that takes in a state object and a compressed frame, and the output is a transformed state object and an image for display on the screen. So that, if you want to decode a series of compressed frames, you just thread the state through. You just run it again on the new state, and then you'd run it yet again on the new state, et cetera, each time feeding in the new frame. So that's our decode function. And we have a corresponding encode function that can encode given any state. So again, the state is a formal parameter of the system, and it's there's no hidden state that you can start encoding from midstream. And then we have this trick here, which is a way to rewrite frames that were encoded based on one state to write them efficiently in terms of a different state, a slightly different state. So this is kind of like what happens in Git. Like if you have a repository that's in a certain state, and you have 1,000 software developers each make their own commit on top of that state, then you can pretty efficiently rebase all those 1,000 commits into one linear history after they've been committed. Does that make sense? So that's why we call it rebase. So that's basically how this works. So we divide the job of encoding into sort of two parts. There's the hard part, the slow part, which we do in parallel, and then we rebase all those slow parts together in order to have one video that's playable, but it only has one keyframe. So I'll show you how that happens. So we have these different threads here. So the step one is for each thread to download sort of a chunk of raw video, and then encode them just traditionally with a keyframe at the beginning of each one. So now we have all these extra keyframes. That's step one. And then the rest is going to be to sort of get rid of these keyframes. So the first thing we do is we take this state object, which, yeah, it's a big object, but that's OK, because we're on Amazon's network. And we just grab it. We figure out what the state is, and we send it to the next thread. So that's the inter-process communication. And then we re-encode each. This is where we rebase. Well, we re-encode this first keyframe instead to be an inner frame in terms of that state that was sent. So we used to have a keyframe, and we do that encode given the state to rewrite it as an inner frame. So this is still in parallel. And then we rebase each chunk onto the previous portion. So we do that. So it used to be like that, and we do that, and then we do that, and then we do that. So there's a serial rebasing step where we rewrite these frames in terms of the state. So that's basically how the algorithm works. There's the slow part, which is done in parallel, and then there's this rebasing, which is done serially. So you can vary the number of frames in each chunk to the number of chunks that get rebased together. I'm going to show you just sort of one configuration. So this is a graph of, again, one of these 2D graphs. So this is how the quality gets better as you give more bits to the encoded output. Yes?
Does a change propagate forward through each segment?
Yeah.
Then why isn't that fairly slow? I guess does it propagate only between threads or within what each thread has already done?
They don't recompute. They just.
Anything. So then why couldn't you do it all the rebasing in parallel? Not that it matters.
Well, the residue does change. So we recompute the residue, but we don't recompute the hard part, which is the motion vectors. All right, so let's look at it. So this is as the bit rate gets higher, how does the quality get higher? So this this blue line is the best you could do. This is Google's production encoder running with a single thread. The quality gets better as the bit rate gets better. And then this orange line is Google's multi-threaded encoder with the maximum parallelism, which happens to be 32. So there's a penalty for this parallelism, again, because for the reasons we've discussed. This is actually parallelism within a frame. So what if we just do the totally stupid thing and we encode 6-frame chunks with no rebasing? So we have a keyframe every 6 frames we force. So then we get really bad results. The quality is very low for the bit rate. OK, so what if we do the same 6-frame chunks, but then we rebase strings of 16 chunks together? Then we're actually able to match the performance of Google's encoder. So that's on the quality. Now let's talk about the speed. So the best you could possibly do for a 15-minute video, this is the Sintel video, the best you could possibly do is 7.5 hours. If you run the multi-thread encoder, it's 2.5 hours. If you run it with infinity parallelism, but a conventional encoder, so we just upload this video to YouTube. They have infinity computers, but they don't have the encoder. That takes 37 minutes. And if you do it our way, you spend $6, it takes 2.5 minutes. You do have to spend the $6. So that's sort of the time results. So ultimately, we have this framework to run sort of 5,000-way instantly parallel jobs. And number 2, we have this purely functional video codec for this massive fine-grained parallelism. So ultimately, I think that anytime you have lots of data and you want results quickly, you're going to end up with this sort of functional abstraction, because you're going to need to be splitting it into millions of tiny little pieces, and you're going to want to run it on something like AWS Lambda or one of these services. I think you're going to see video filters and any sort of 3D rendering and compilation and any sort of machine learning or data visualization or searching. I mean, Google Search is like a very parallel task. All of these jobs are going to end up having to make functional or granular, and so that we can run them many way parallel. All right, any questions on that system? Yes, sir.
You didn't talk about network acceleration or the network latency or the network bandwidth affecting your process. It doesn't have any effect?
Well, we have to pay the penalty of sending all these objects around within the Amazon LAN, absolutely.
Do you have any idea for how much it impacts your performance?
I do. I have a slide. Maybe we could get to this at the end and
okay,
if I
sure.
have time. But yes, the answer is the computation is the big burden in this one.
Okay.
Yes.
$6 compared to what for multi-threaded, for example?
So for the multi-threaded on EC2, It's probably, I don't know. It's the same order, I would say. For the YouTube, I definitely don't know.
It's focused on the lambda computation. That's the $6.
Yeah, exactly. Yeah. Okay, great. Well, let's talk about the next one, which is real-time video. So same, it's going to be the same trick. You can leave now. You won't have lost anything. All right. So let's talk about the interfaces. You know, we've hit on the video people for a while. Let's talk about our problem. What are the interfaces exposed by the transport layer? So this is kind of how video people see the network. There's a sender, the receiver, and then in between there's some bandwidth, which is like a horrible term for any capacity measured in bits per second, but that's somehow what we use. So let's talk about if you're writing a network application, what are the questions you can ask the transport layer? Can you say, can I send 1 byte without blocking? Is this something the transport layer will tell you yes or no answer to? I think it's yes. Yeah, how would you do it?
Oh yeah, you send non-block and then.
Yeah, you can poll, and when the poll says that your socket is writable, then you know you can send 1 byte without blocking.
But blocking where?
For the application. The transport layer will take your byte.
Okay.
Okay, what if you want to say send as many of these bytes as possible?
Well, it's not well defined.
Well, you can do a non-blocking write, and then write will tell you, you can non-blocking write a megabyte, and write will come back and say, I wrote a kilobyte.
But it doesn't mean that they send it, right? So that's only putting it in the kernel buffer. So
Yeah, that's true. That's the interface.
Okay, you can even, it turns out you can even say, what is X? That's a question you can ask. There's an interface for that in WebRTC. It's a standardized RFC for that. How about a very dumb question? How much can I send now without blocking? You know, if I were to do a non-blocking write, how many bytes would you actually take before I write them? Is that a question you can ask?
No.
Yeah, I don't think you can do it. I don't think there's any sort of POSIX way to ask this question.
What do you mean? You write
Try.
with the biggest buffer you have.
Oh yeah, that is not the same thing. Because once you've written to a stream socket, you've committed to those bytes. There's no way to change what you're going to do based on the answer to this question. And so an application that's maybe a file transfer or something, you know, it doesn't care. It's going to write the whole file eventually. But a video application does care how many bytes it's going to be allowed to write before it writes them. And the fact that you can't ask this question has caused a lot of problems. So the current video conferencing systems and real-time video systems, they really don't work well when there's any uncertainty about the answer to that question, uncertainty about the network. Because the way, you know, Skype or FaceTime or Hangouts or even WebRTC works is the transport layer tells the encoder, you know, here's the bit rate you should target, which is sort of this X. And then like a lot of time passes, and then the encoder delivers a frame, and the transport is stuck sending whatever the encoder created. Even if the encoder overshot the bit rate it was told, which happens all the time because it's very difficult to write a video encoder that correctly, you know, hits an a priori bit rate, you have to send it, and that blows up the delay, you know, or it causes loss. Or what if the network has changed in between while these milliseconds were passing? You still have to send it, and that blows up the delay. So this is a problem for sort of Skype and FaceTime and Hangouts and all these applications. And let's say you're the kind of person that like makes new congestion control schemes, as a lot of people in this room are. Let's say you invent a brilliant one that's totally appropriate for these applications. This is why this is a good problem for academics. Is like, let's say you go talk to the vendor. You know, you go talk to Skype or Google, and you say, hey, here's a new congestion control scheme. You should totally adopt it. Here's what they'll say. They say, oh, we can't do that because our software codec was licensed from another company. Microsoft was licensed their codec from Google, and it doesn't support that interface, so we can't do it. Or our hardware codecs don't support that interface, and we have to support 50 different manufacturers. This is what Netflix will tell you. Or our pluggable congestion control interface, you know, pluggable modules doesn't support that interface. Or it doesn't matter because the other companies work the same way. So the companies are not going to solve this problem, no matter, like you can take a pig to water, but you can't make better video conferencing systems. Because like they're not, there's no pressure on them to be crazy and to try and do a sort of like to push the boundaries about where these layers are. So that's why it's a great problem for us. So we built a sort of co-designed congestion control protocol and video codec. So there's a video-aware congestion control and there's a network-aware video codec. So the goal here is to have the traffic more closely match the evolving capacity of the network. So there's sort of 3 problems of trying to do this. Problem number 1 is there's sort of no data that the codec gets about how big a frame it can send without blocking. So you know, we need sort of video-aware congestion control. Problem 2 is the current video codecs, even if you had this information, there's no way to make them hit the right size. You know, even if you knew the congestion window, there's no way to have the codec produce a frame that's that size. So you need a way to do that. And then problem number 3 is our solution is actually that the codec just goes blind and it makes a whole bunch of options, and then you know the transport picks one as the winner that ends up matching the congestion window and sends it. Problem is, even if you can do that, there's no way to then mix and match the output of these different streams. You have different options. You pick a winner, but then you're kind of stuck with that encoder going forward. So you actually need this functional video codec to be able to make that work. So let me talk about those 3 problems in turn. Problem number 1, there's no way to tell the codec how big a frame should be sent right now. So we have a transfer protocol that tries to estimate what should be the size, the coded length of the next frame that we think the network can handle without dropping or sort of excessively queuing. And one issue we had to deal with is that most congestion control protocols are evaluated assuming that the application is full throttle, assuming there's always data available from the application to send. And with a video codec, that's probably not the case because these codecs are bursty. They send a frame, it's maybe 20 kilobytes, and they have to compute for a while before the next frame is ready. And you don't want to, you don't want to have 0 bytes in the socket and then the congestion control protocol say, oh, we need to, deflate the congestion window, which is what will happen with with TCP or something like that. When it's idle, it'll go back to slow start. So you don't want that to happen. So instead, we sort of explicitly treat that in the congestion control. So the sender is sending like a bunch of packets here, and then there's some wait time, and then a bunch of packets here. These represent 2 different video frames. And when they get to the receiver, they're spread out by whatever the bottleneck capacity of the network path is. So there's some packets here, and there's some packets here. And we want the receiver to try and infer the rate that packets are arriving, but we don't want it to get confused by this idle period. So we have the receiver pause its inference during this idle period. So the sender actually announces at the header of every packet how long it's been since it sent the previous packet. And we have the receiver forgive the same amount of time. It just pauses the inference when this interval is happening. So it doesn't assume that just because it's not getting any packets that the capacity must be 0 until this grace period has elapsed. All right, so other than that, the receiver maintains a moving average of the inter-arrival time of the different packets to guess sort of how fast can data get to the receiver. And then we have a sort of packet accounting technique where the sender says, okay, well, you're telling me packets are arriving at 1 packet per millisecond. Meanwhile, I've already sent you 60 packets that are unacknowledged. So there's already 60 milliseconds of packets in the queue. So if I sent you another packet, it would probably take 61 milliseconds to arrive. So it's sort of this accounting combined with this estimate. You look quizzical, Michael.
No, I'm just wondering aren't you indirectly solving the fact that TCP is bursty? Because if you had something that was based on pacing in the transport layer, wouldn't much of this go away?
Well, we do pace also in the transport. I mean, we're the transport layer.
But basically, right, any congestion control
No,
program
but
paces, right?
But this is a different problem, which is that the application does not always have data available to the transport.
The content is dynamically adjusted itself to the channel. Yeah. So it's a magic.
Yeah. Okay, so that was number 1. So now that's how we get this estimate about how many packets can be sent now. What's the sort of the size that the next frame can be? We have some maximum target delay we're willing to tolerate. Let's say 100 milliseconds. We subtract from that what we think the delay already in the network is, which is sort of how many packets are already in flight times whatever we think this inter-arrival time is, and then that governs how many more packets we can put in the buffer in the network without exceeding that delay target. So that's our target for the frame size. So problem number 2 is even if we know how big the next frame should be, there's no way to get a codec to produce a frame of that size. And this is a real problem because you sort of have to try encoding it before you know like how big it's going to be. So instead, we just use parallelism to solve this problem. We encode, in this version, 8 different versions of the frame with all kinds of different options. And we're just going to see after the fact how big they end up being. And the transport can actually late bind the decision of which version to send. It can say, okay, well, the congestion window right now is 40 kilobytes. Not when I told you to start the encode, but after the encode is finished, what's the contemporary value of the congestion window? Yes, sir?
How awful does the resulting video look? Because you're basically playing with the quality on a frame-by-frame basis.
That's a great question. Well, it's a great question. So let me get to that. So problem number 3 is that even if you have these multiple encoders running in parallel at different qualities, there's no way to sort of mix and match the result of their output. Because again, if you only have this interface, you have these automata, but these frames are bound to the source and target states. You can't just pluck frames and apply them to some other state. So let's say we're up here, and we take this, we pick option A1, we pick this edge. Now the decoder is going to be in this state, and we're stuck. The only option we can send next is B1. There's no way to send B2 or B3, the sort of lower quality frames, because we're in this state. The only way to switch would be with a keyframe. And the keyframes are huge. We don't want to send a keyframe. So how do we fix this? Well, it's the same trick. We need explicit state passing style. We need to be able to start encoding from midstream so that we can pick a particular winner and then tell each of our 8 decoder threads, hey, that's the winner. start your next frame assuming that that state was received by the receiver. So ultimately, the transfer tells the encoder, okay, give me the next frame, and the encoder produces a bunch of options. You know, maybe there's one that's big and one that's sort of the same size as last time and one that's worse. Each one is going to result in a different target state of the automaton, and the transport will pick one. It will late bind the choice to pick one, and then it'll tell the encoder, hey, I sent this option. Now I want you to fire off your 8 encoding threads, but assume that this state is the one that got received by the receiver. So then there's more options. And then we pick one, and there's some more options. We pick one, there's some more options. So to be able to do this, you need to have the explicit state passing encoder. You need to be able to start encoding in midstream. Otherwise, you just have sort of 8 parallel options. There's no way to navigate among them. All right.
The next block is additive regardless of it's better or worse or the same.
How do you mean?
You have something that relying on the previous state.
Yes.
The previous state is
Well, we have a lot
created for a better or the same or
Yes, that's true.
or worse quality.
Yes.
So this delta is working regardless.
Well, that's the idea. If a packet gets lost, though, then the receiver doesn't end up in the state we thought it was going to end up in. So we deal with that sort of also in a state passing way. We have to say, okay, we're wrong. It wasn't in this state. It's in some other state. Deal with that. So we have a loss recovery strategy that I won't get into. All right, so we did an end-to-end evaluation of the system. I'm not sure everyone's ever done it like this before, but we have a reproducible input video and reproducible network traces, and we want to run unmodified versions of Skype, FaceTime, Hangouts, and WebRTC. We're not going to change their code at all. And then, of course, our own system. So to do this, the students built this crazy setup here where we have a real video of some people having a video chat, but we put barcodes in the upper left and lower right corner of every frame that tag the ID of that frame. It's a unique 64-bit barcode. And then we put that out a very special HDMI card that has millisecond timestamp accuracy. So we know exactly when the frame left our test system. And it goes through this synthetic webcam. So it converts it from HDMI to make it appear like a USB webcam. And we plug that USB jack into a Mac or a Windows or a Linux or an arbitrary computer, and it thinks it's getting video from a webcam. It's not. It's getting our crazy barcoded video, but it thinks it's getting webcam video. And then that computer, which is totally unmodified, sends data over the network, and it goes through a network emulator, which we also control, and the network emulation is synchronized with the test video. And then it goes to the receiver, which is also an unmodified Mac or Linux or Windows computer, and it comes out that computer's display on an HDMI port, and we full screen the display, and we put the HDMI port back into an HDMI capture card in this computer, which again is synchronized with what's sent out, and we have sub-millisecond accuracy, very low jitter, because it's a hardware timestamp on when the frame came in. We are storing the raw video that's being sent out and the raw video that's being received, and then in post-processing we match up the barcodes. These are very big barcodes, so it's comprehensible even going through lossy video compression. We match up the barcodes to find the corresponding frames to get the totally end-to-end frame delay, and then once we have the corresponding frames, we measure the visual fidelity between what was sent and what was received, the end-to-end visual quality. So let me first show you just some network results. So here's what happens over a synthetic network outage. So this is not real data, this is totally synthetic, but the network gets worse, then it gets better. So if we look at Skype or WebRTC, for example, they don't respond quickly enough to the network outage. Because for them to change the bit rate of the video encoder is a big deal. So they both, the blue line and the green line, they both infringe on this bad time. Whereas our system, Salsify, is able to get underneath the bad times and then to recover quickly after. So that's what happens. This is a sort of congestion control result. So let's look what happens to the video frames during the same event. So every dot here is an individual video frame that we're tracking the delay of. So our system actually doesn't have the best delay when things are good, but we recover much faster after the outage is over than either WebRTC or Skype. So Skype takes a very long time to recover here. It's like, it's maybe 3 seconds. And WebRTC totally freaks out. It just stops sending frames at all. Here's a frame here, and then here's a frame here, and it just totally freaks out. So that's on the frame delay. So if we look at both the quality and the delay, same kind of graph. So the best quality is up here, and the best delay is over here, because we flipped the x-axis. Salsify ends up getting lower delay and higher quality than any of the incumbents. And I should stress this is a video encoder that was written by one grad student in 3 months. So it's not like a state-of-the-art video encoder. And it's the VP8 format. Some of these guys are using H.264, H.265, or VP9, more sophisticated codecs. But I mean, I guess it's a chauvinistic thing to say, but I think that what this proves is that the codec is good enough already. And that the way to improve video conferencing is not by continuing to make the codec better and better. Taking the codec from 98 to 99 is not the bottleneck. The hard part is us. It's the network layer, or really it's the interface between the codec and the network. That's where that's where the problems are, and that's where the gains are going to come. Yeah. So here's over a Verizon emulated Verizon network. Here's over an emulated AT&T network. These are all U.S. cellular carriers. Same kind of thing. Here's over a very bad link. This is a UMTS link, so not even LTE. So yeah, that's sort of the numerical result. So the takeaways here, we needed that functional interface to the codec to be able to match the capacity of the network. And we needed that richer interface to the transport to get sort of how many bytes can I send right now. Now, this is not actually usable, right? Because no one wants to burn 8 cores on their video conferencing. People want to use hardware encoders. And hardware encoders in principle could do this, but they don't support this interface. So I think there's no time like the present to persuade the people that make these hardware encoders that it's valuable to expose state as a first-class object. I think the only way to persuade them is to show empirically that it's beneficial. But that's sort of the result that we have. Any questions? All right, should I just soldier on? I maybe have maybe 5 more minutes. Is that all right? Okay. All right, let's do it. So we did the image compression, we did the video compression, we did the real-time video compression. So here's our speculative work, which is we're trying to do sort of software compilation. So there's that XKCD, I should have had it here, about my code's compiling. But it takes like a day to compile Chromium on a typical computer. And like Chromium is the application I use most often, and it takes so long to compile it. Wouldn't it be nice if you could type sort of make-j5000, just have it take place instantly in the cloud? What was that, sir?
I mean, the dependency tree may not be that wide eventually.
We think it's like a few hundred wide for most of the time. It depends how, you're absolutely right. Well, so, okay. So the goal is to distribute builds across sort of 5,000 cores in the cloud without modifying the build system. So Google and Facebook both have competing ultra-parallel build systems, but they only work if you somehow persuade the developers to change their build system to use your parallel thing, which, even Google has not persuaded basically anybody outside Google to use their system. So our approach is to instead reverse engineer the actual dependency graph in an existing makefile or CMake or Ninja file. And then discover, sort of by lazy execution, what the true dependencies are. So that, anyway, the goal here is locally run the build system, run Make or Ninja or whatever, but don't actually compile anything. Just run simulations of the preprocessor, the compiler, the assembler, the linker, and ultimately write out a thunk, a delayed execution, a closure that says, hey, this file, the file could be called Chromium, but what we're really going to say is, this is the file that you would get if you ran GCC on these inputs that have these hashes. And that could be another thunk. You could have had to run GCC on some other thing. So there's ultimately a dependency tree that's captured by, can I say symbolically executing GCC? Is he here? Yeah, can I call it symbolically executing? No. Fake executing, lazily executing? That's different from symbolic. It's not symbolic. Well, okay, well, here's what it looks like. This is what we actually write on the disk. So, if you ran GCC-O, testfile.o, testfile.i, what we get is, instead of the output, like an object file, we get this thing, which says, hey, the function is run GCC with these arguments, and the input files, the dependencies, is this remake.i that has this hash, and then the output is going to be this file. So that's what the thunk looks like. It's still not symbolic execution? No? Okay. But it's lazy, it's delayed execution. So we capture the exact functional footprint, the sort of dependencies of this function, with hashes so that later we could run it either locally or in the cloud and get a deterministic output. And we have a sort of sandbox that makes sure that it only reads the files that it's supposed to read, et cetera. So yeah, these thunks are self-contained. They can be forced either locally or in the cloud. The goal is to run sort of 5,000 thunks in parallel. And in fact, the goal is to be able to trust other people's assertions. So if someone tells me, hey, you're looking for the file with this hash, and I have it, I might just trust everyone with that claim, right? At least by default. Because if someone lies to me, I can detect it immediately. I download the file, hey, the hash wasn't what you said it was, you're a liar. And in fact, I can expose them publicly. I can say, Costin posted that the hash was this. He is wrong, and the whole world can stop trusting you. So that's a very easy thing to trust. I might want to be a little more selective with a different kind of assertion, which is, hey, the thunk with this hash, this thunk, if you actually run it, it evaluates to this result. Now, I still want to probably trust people. Yes?
What I don't get is, how do you calculate a hash for a file that you didn't create yet?
Well, we calculate the hash of the thunk. And then later, when the thunk is resolved, we can write a new cache entry.
So the hash is of the thunk, which is this blob of information.
Yes.
So
here you see the in file.
Why can't I just fake it? if I want to.
Well, because if I ever, okay, so let's say you put an entry in your cache and I'm trusting you, and you say, hey, the output of evaluating this, this thing is something else. I might trust you, but I could always prove, you're always going to be at risk of getting caught. Because if I decide to double check you, I can run this thunk myself. And if it gets a different output, I can tell everyone, like, hey, I took the liberty of double checking this gentleman, and I think he's a liar. And other people can verify that. So it's not quite as easy to detect the invalid claims, but you're still putting yourself out there at risk of being embarrassed.
So what if you have like multiple layers in a chain? How can you pinpoint like which one's lying and which not, right?
Yeah.
It's like
Well, let me finish the talk. We can talk about this maybe offline. So ultimately, look, bottom line here is that everyone wants to do things interactively, and there's a lot of data. There's big data, and there's people, very demanding people. And ultimately, what that means is we're going to need granular interfaces to everything. We're going to need a lot of parallelism, and ultimately that means sort of functional programming. And not maybe real functional programming or real symbolic execution, but these sorts of fake concepts that I'm pretending that I know what I'm talking about. But that's what's going to enable the new applications. It's worth refactoring these interfaces. Like between the codec and the transport, we should really rethink this. The transport we can do better to expose more information to the application. The application can do a lot better to expose more granular interfaces to us. This ability to save and restore program states turns out to be a very powerful tool in image compression, in video compression, in real-time video, in compilation. And in fact, even Dima's work is ultimately about starting an SSH connection from a trusted host, locking down what it's going to be able to do by sending the command and then the no more sessions, and then only once you've limited authority, then freezing the state of the SSH connection and restoring it somewhere else where you actually have the data, but you want to have this lockdown thing. So ultimately, everything is about being explicit about state. Thank you to HebrewU for bringing me here and everyone else.